Is it all right? Are you able?
Yes, sir.
Yes, sir.
So yesterday I talked about quasi-linear partial differential equation of first order. I told you it appears very simple.
Sir, zoom.
Sir, you can maximize a little bit.
This is, I think this is the maximum.
Yeah, no, it's okay, sir. It's okay.
Okay. So this is, I told you that this quasi-linear partial differential equation, it looks very simple, but it's quite deceptive. I mean, a solution of this one, I mean, if one has understood this, the basic essentials of this partial differential equation, then in fact one knows about the hyperbolic theory of hyperbolic systems. So you see it differs from the linear equation. You may recall in the linear equation, the C was a constant. This was constant, right? In the linear case, the C was constant. And we noticed that the solution, in fact, it is transmitted from one part of the medium to another part with a constant speed, right? With a constant speed without any change in its shape. If this is the initial profile, u is equal to u naught x, then this profile, in fact, it moves to the right with the speed dx is equal to c. C is the characteristic speed. The characteristics emanating from each point of the profile, each point on the profile along the characteristic direction, and we get a profile, I mean, at later times, which remains of the same shape. So, right? This is the linear case. But here, C depends on U, right? In the quasi-linear. So this is the difference between linear and non-linear. Here, the speed depends on U. So obviously, we expect that this initial profile will undergo a distortion during the course of propagation as t increases. Why? Because here dx dt is constant. That is, each point, I mean, the profile at any time t can be obtained from the initial profile just by displacing each point on the profile a distance c naught t towards right. Correct? Each point, okay? But here c depends on u. C depends on u means suppose this is the u axis. So if I take this c dash c to be an increasing function of u, okay? If I take C to be an increasing function of u, then on this part of the profile, you can see here, if this is your initial profile, and this is u direction, this is your x direction, and this is your u naught x at t equal to 0, right? This is the initial profile. U is equal to u naught x at t equal to 0. This is the initial profile. Now, what will happen if C is an increasing function of u? Look here, if this is the initial profile, we would like to know actually what happens to the profile at later time. So you can see here, of course, the solution is going to be the same. Here in this case, the solution was, if you remember, u is equal to u naught of x minus ct, right? At t equal to 0, u is equal to u naught x. You can see here that it satisfies the initial condition, right? It satisfies the differential equation identically. So in fact, this is a unique solution of this initial value problem when c is a constant, and it shows that the profile moves with a constant speed without any change in its shape, when it is linear. But if it is quasi-linear means this c is a function of u. What is c? The characteristics. dx dt is equal to c of u. Along these curves, along these curves in the xt plane, of course, u remains constant. U remains constant because left-hand side is nothing but du dt. So u remains constant along these characteristic curves. And if u remains constant, this right-hand side is constant. You can see here that x is equal to xi plus t times c of, yes, u remains constant. So what is you can see here, what is that constant? This is any characteristic issuing from this point, and it meets the line. This is your xt plane. This is your xt plane. So at t equal to 0, it meets the line at x is equal to xi, right? At t equal to 0, x is equal to xi. And what is the value of u here at t equal to 0? Whatever the information is available here. So u is equal to u naught of xi. Is that right? Because this is the initial condition. Is it all right? This is the characteristic, and this characteristic through xt meets the line t equal to 0 at x is equal to xi. So whatever the information is available here, that information is transmitted along that characteristic. U is right. U is equal to u naught xi. So this value which is available here at t equal to 0, it remains throughout this characteristic. That is, at any point t, the value is u is equal to u naught xi. Is that right? Hello? So u equal to u naught xi, you can see here. So c u naught xi and hello?
Yes, sir.
Yeah, this is the solution. So you see, this is the analytical form of the solution. This is your analytical solution. Analytical solution to this initial value problem. I will call this as 1. This is quasi-linear. This is the partial differential equation. This is the initial condition, right? You can see here that xi is the parameter. By the way, what did I say in the beginning? What are these characteristics? These characteristics span the solution surface. So here you can see what do you mean by span the solution surface? The union of all these characteristic curves. So if I eliminate xi from these two equations, in fact, it is the locus of that characteristic. So you can see here what is the locus? U is equal to u naught of xi. What is xi? Xi is equal to, transposing this term to the left, that is x minus t times c of u. So this is the solution at any time t. This is the solution at any time t, right? You can see quickly that at t equal to 0, it satisfies the initial condition. At t equal to 0, it satisfies the initial condition that u is equal to u naught x, right? And it satisfies this condition. I think we did it with this calculation. You can, again, I can do it. What is ut? Ut will be your u naught prime. Prime means derivative with respect to this argument function. Multiplied by, yes, using chain rule, it's t derivative. That is minus c of u. Is that right? Minus c, it's derivative with respect to t, 1. Minus t times c prime. C prime means derivative with respect to u, and then the derivative of u with respect to t. Is that right? ut. Chain rule. So this is transposing this term to the left. We noticed yesterday that it turns out to be 1 plus t c dash u naught dash ut. This is equal to minus c u naught dash. Is that right? This is equation number 1. Similarly, if I differentiate this, let us call this as 1. So I will call this as 2. This is the solution. Let me call this as equation number 3. Now, what is ux? Ux will be your, again, u naught dash. Its derivative with respect to this argument function x minus tcu. Right? You can put this is equal to tau. In fact, this is your xi. This is clear, right? U naught dash into its partial derivative with respect to x. So what we will get? Partial derivative with respect to x means 1 minus t times c dash and ux. Is it all right? Transposing this term to the left, 1 plus t times c dash u naught dash ux. This is equal to u naught dash. This is equation number 4. From 3 and 4, it is clear if I multiply. So let me see here that ut from this, ut is your minus c u naught dash upon 1 plus t c dash u naught dash, and ux is your u naught dash divided by 1 plus t c dash u naught dash. Is that right? What I am going to show that this indeed is a solution of the initial value problem, right, in the neighborhood of the given curve, given space curve. So if I multiply this equation by C and add to this, what do we get? Ut plus Cux. Look here, C u naught dash upon this minus C u naught dash upon same expression. This turns out to be 0. These two equations, they imply that U is such that it satisfies the differential equation 1 identically. Is that right? Hello?
Yes, sir. Yes, sir.
So this is indeed is a unique solution of the in the neighborhood of the character. You see, this is your space curve. This is your space curve. U is equal to u naught x. This is your space curve, and this is your characteristic. In the neighborhood of this space curve, we have got the solution. Right? This solution is of class C1. As so long as this is different from 0, right? We noticed because it is the implicit form of the solution, right? It is the implicit form of the solution. So it is very clear that this solution is of class C1 as long as this is different from 0. Implicit function theorem, I told you last time, it says that xi can be expressed as a function of x and t. From here, xi can be expressed as a function of x and t provided. What is the condition? Yes, you see, last time I told you that this function x t xi, this x t xi is your xi plus t times c, which is a function of u naught xi minus x. This is equal to 0. This is the function which vanishes at some point x t xi, right? Implicit function theorem says that if it is a differentiable function, which is so, because C is assumed to be differentiable, U naught is assumed to be differentiable, so it's a differentiable function, right? At that point where it is 0 in the neighborhood of that also, right? So it is very clear, implicit function theorem says that xi can be expressed as a function of x and t, xi can be expressed as a function of x and t uniquely in the neighborhood of this point, provided the partial derivative of this with respect to xi is not equal to 0. And this condition tells us what? 1 plus t c naught dash into u naught dash xi not equal to 0. Precisely the same condition. You see, the denominator should be different from 0. So in order that we get a differentiable solution, right? A solution which is of class C1, that is ut and ux, they are also continuous. This condition must hold 1 plus t c naught dash u naught dash xi equal to 0. So what does it mean? This condition tells us that c naught dash into u naught dash, if these, right, if this expression c naught dash into u naught dash, if c naught dash and u naught dash, if they are of the same sign, then it is never 0. Because t is always positive. Hello?
Yes, sir. Yes, sir.
T is always positive. C naught dash, U naught dash. If C naught dash is positive, U naught dash is positive, this is positive, T is positive, okay? So this expression is never, this condition is always satisfied, right? The problem arises when they are of opposite sign. The problem arises when they are of opposite sign. C naught dash, that is C is an increasing function of U. So here you see we have assumed that C is an increasing function of U. So this C is all right, we have taken to be, this is always positive. C naught dash is what, this is always positive, right? This is always positive. But initial profile, if this is the form of the initial profile, look here, on this part of the profile, U naught dash, the tangent, right? It has a positive slope. Is that right? So this is positive, but here on this part of the profile, U naught dash will be negative, correct? And therefore, if they are of opposite sign, so at every point on this part of the profile, where U is a decreasing, U naught x is a decreasing function of x, on this part of the profile, this will be negative, and therefore at t is equal to minus 1 upon c naught dash into u naught dash psi, yes, the solution breaks down. When this vanishes, the derivatives become unbounded, that is, the continuity of the solution breaks down. This is what the analytical form of the solution says, but actually this is correct. You see, from this interpretation also, look here, what I say, on this part of the profile, C is an increasing function of x, right? On this part of the profile, C is an increasing function of x. And therefore, the particles, yes, they will move along the characteristic. Is that right? But it is clear that higher values, because C is an increasing function of u, so higher values of u will propagate faster. Am I right? Because dx dt is C of u. If u is large, right, the point located here will move faster as compared to the point located here. Am I right? Higher values of u, they propagate faster than the lower ones. Is that right? Hello?
Yes, sir.
So what will happen? The result would be, the consequence would be that this part of the profile will flatten at some time. Is that right? Because the distance covered by this point would be larger than the distance covered by this point as compared to the distance covered by this point, and so on. Is it all right? This part of the profile flattens during the course of propagation because the higher values of u, they propagate faster. But what will happen to this part of the profile where u is a decreasing function of x? On this part of the profile, tell me what will happen? Hello? It will steepen. Hello?
Yes, sir.
Because it's very clear. Because you see, the points which are at the rear part of the profile, the points which are in the rear part of the profile, they will propagate faster. You see, these points will propagate faster, but as compared to this, and therefore, this part of the profile will steepen. And after a finite time, what will happen? Yes, it will develop a vertical slope. Profile will develop a vertical slope. Is that right?
Yes, sir.
And beyond this, it is very clear because the higher values, they propagate faster. So the profile will fold into itself after a finite time. So this is the scenario you see at later times. This is the scenario. The first breaking takes place here. This is TB. What happens at this point? At this point, actually, this type of behavior, which is quite evident physically, it is predicted by the analytical form of the solution. Can you see? Our simple argument says that yes, this phase of the profile where C is an increasing function of u, because here u is an increasing function and C is a function of u, right? I have taken C dash to be positive. So that is, whereas this part of the profile, it steepens. Is that right? This should be the behavior, and exactly the same behavior is shown by the analytical form of the solution. It is confirmed, right? So this is a perfect model, no doubt about it. Is it clear to all of you? Hello?
Yes, sir.
Any point which needs any clarification? So this is a remarkable thing. If it is a linear equation, the profile undergoes, yes, when it propagates, there is no distortion in the profile. But if it is quasi-linear, if the differential equation is quasi-linear, then we find that if this is the expansive phase, because on this part of the profile, C is an increasing function, this flattens, whereas this is the compressive phase of the profile. I say it is a compressive phase because it steepens. Is that right? Hello? Here C is a decreasing function. Here C is a decreasing function. C is the velocity. If the velocity decreases, naturally, I will say that it is the compressive phase. If the velocity increases, I would say it is the expansive phase. So here the profile consists of expansive phase and a compressive phase. The expansive phase flattens, right, during propagation, whereas compressive phase steepens, and in fact it develops a vertical slope after a finite time TV. And we have seen that this behavior is exhibited by the analytical form of the solution. Is it all right? Hello?
Yes, sir.
Okay. So this is something which is very important and quite distinct. So this equation is quite different from the linear one. In the linear case, it doesn't happen. But in the quasi-linear, this solution breaks down after a finite time. Let us see what happens. So let me say, for the sake of simplicity, I will call this as minus 1 upon f dash. It is a function of, right? What is the c? C dash. C dash is nothing but c is a function of what? C is a function of u. And what is u? U is equal to u naught xi. So c is a function of u naught xi, but of course u naught xi is, we have said this thing, that u is equal to u naught xi along the characteristic. Is that right? That is u of xt at any time t is equal to u naught xi. This remains constant. Whatever the information is available here, this uxt at any time t, right? It is u naught xi. So actually, if we know the solution at this point, we know the solution at every point of this characteristic. All right. So I will call this as f dash. What is f? F is your C u of xi, is that right? C of u naught of xi. If I take f is equal to, just, I mean, for the sake of simplicity in the expression, I take this expression, T C of u. What is u? U is equal to u naught xi, is that right? U is equal to u naught xi. It's quite clear from here. So C u naught xi, I have called this as capital F of xi. And if it is capital F of xi, the derivative of C would be what? Hello? This will be your F. If F is this, then F dash will be C dash into U naught dash xi. So I think this is a simple expression as compared to this, but we should always remember that F, this entity is nothing but C dash multiplied by U naught dash. What is C? What is F? F is C of U. What is C? C is the speed with which the points on the profile, they propagate along the characteristic. This is called the characteristic speed. This is to be kept in mind. So you see, if we are given an initial value problem, which is quasi-linear, then we can find out the time when the solution breaks down. In the neighborhood of space curve, perhaps the solution may be, this is smooth. This is, I again repeat, the solution is smooth as long as this is different from zero. But this vanishes at t is equal to this. So away from this, in the neighborhood of gamma, this is your space curve. In the neighborhood of gamma, you get a unique solution which is of class C1. But as you move away from here, this solution, in fact, yes, the continuity of the solution breaks down. The gradients become infinite. And when the gradients become infinite, the continuity of the solution becomes discontinuous. Hello? Is it all right? Or there is a question from your side? Hello?
So no question.
Yeah. Yes, please. Okay. So let us see what happens in the xt plane. This is what we have observed in the ux plane. This is what we have observed in the ux plane, that if the profile is like this, right, it has some expansive phase, some compressive phase, then actually it undergoes distortion, and after a finite time, it develops into a discontinuity. But if the profile is just expansive, that is C dash and U dash, they are of the same sign. If this is the initial, say, profile, if I take, say, this is the profile, for example, there won't be any breakdown. because it is an increasing function, right? For an increasing function, C naught dash and U naught dash both are of the same sign. It will, right? This expression will never vanish. Is that right? But if it is compressive in nature, if I take the profile to be like this, if this is the initial profile, then at every point on this part of the profile, the solution will break down after a finite time. And in fact, this expression enables me to determine what is the breaking time. Is that right? Hello?
Yes, sir.
Let us see what happens in the XT plane. So in the XT plane, I can use this. All right. So in the XT plane, let us see what happens. This is your XT plane. This is your XT plane, right? So if suppose this is the profile in the UX plane corresponding to, suppose these are the points, say xi1, these are the points, yes, xi3 and xi4. Right? I mean, this point, the value of u is right somewhere here. So you see, this is your UX plane and this is your XT plane. UX plane is this, right? This is your U and this is your X. There is no need of writing this, but just for the sake, I think it would be better if I write just below it. It makes sense. This is your xi1, this is your xi2, this is your xi3, this is your xi4. I think this is better. UX plane, this is the profile. Let us see what happens in the XT plane. Now, can you, yes, you can see here that this is the point corresponding to xi1 and xi2, right here. This is your xi3, this is your xi4. What is the relation? I know that dx dt is equal to C of u, okay? And C is an increasing function of u. This is what I have taken as a smooth function, such that, right, C dash is positive. So look here, here the value of u is the value of e here, hello? Right? The value of u here is greater than the value here. Somebody is talking on, yes, mic perhaps maybe taken care of. I think that others, they don't get disturbed. C dash u is positive, so look here, you look at this point. This is the higher value of u, right? Here u is bigger than this. So what will happen? This point on the profile will propagate faster than this. Is that right? Hello? That is dx dt at this point, dx dt is this point, is greater than dx dt at this point. Is that right?
Yes, sir. That's right.
So now, can you tell me what will happen to the slope? Dx dt is the speed. What is the slope? Slope will be dt dx. Hello? Just the reciprocal of this. Am I right? In that,
yes,
dt dx is your slope. Slope is 1 upon C of u. So it is very clear that the slope of the characteristic issuing from this point would be less than the slope of the characteristic issuing from this point. And as a result, the characteristics issuing from these 2 points, they will diverge in the plus t direction. They will diverge. Is that right? Because the speed of this is greater than dx dt is greater here as compared to this, and therefore the reciprocal, right, dt dx at this point would be smaller as compared to that expression here. Is that right? What does it mean? It means the characteristics will diverge in the plus t direction, and if the characteristics diverge in the plus, because different characteristics, they carry different information from the initial data, so solution is always of class C1, no problem at all. But what happens here? Let us see. At xi3 and xi4, xi3, it is at a higher value because corresponding to xi3, this is the point on the profile, and here u is greater than this value of u here. Is that right? And we have said that C is an increasing function of u, so it means this will propagate faster than this. and therefore the slope of the characteristic issuing from this will be less than the slope of the characteristic from this, and therefore these two characteristics are bound to intersect after a finite time. Am I right? Hello?
Yes, sir.
Suppose this is the point where they intersect. This is the point x star t. Is that right?
Yes, sir.
If this expansive phase characteristics, they diverge, and as a result, we have a perfectly continuous solution because different characteristics, they carry different values from this initial data at t equal to, here u is equal to u naught of xi1, here u is equal to u naught of xi2, right? So different characteristics, they carry different values, and we have a perfectly smooth solution for all time. But here, the characteristics, right? Here the slope of the characteristic is less than the slope of the characteristic here, and therefore they converge in the plus t direction, and they are bound to intersect at some point. We can find out this point of intersection because I know the equation of the characteristic. X is equal to xi plus t times of f of xi, right? This is the characteristic. What is f? Yes, I have just mentioned that this is your c of u naught of xi. C is a function of u, and u is equal to u naught xi. That is right. It's a part of the analytical solution. F is this. So these are the characteristics. Look here, x star, t star. This point lies on the characteristic issuing from this point. So I will write x star is equal to xi3 plus t times f of xi3. Am I right? Hello? This equation of this characteristic is this. Equation of this characteristic is showing from xi4, right? X star is equal to xi4 plus t times f of xi4. Now from these two equations, if I subtract the later from the former, what do we get? Xi3 minus xi4, right? Divided by what? F of xi4 minus f of xi3. This is with minus sign. This is your t. Am I right? Hello?
Yes, sir.
Am I right? T is equal, because t f of xi3 minus f xi4. Yeah, where this is, I think, f minus 4. Please take care of this sign. So what happens in the limit? In the limit, say if xi3 approaches xi4, in the limit when xi3 approaches xi4, what happens? This is nothing but, in the limit, this is nothing but minus 1 upon f dash at xi4. Am I right? Calculus. Recall the definition of derivative. Okay? F x2 minus f at x1 divided by x2 minus x1. You bring it in the denominator. I can write this as minus 1 upon f of xi3 minus f of xi4 divided by xi3 minus xi4. Is that right? And in the limit when xi3 approaches xi4, yes, what is the limit of this ratio? Yes, it has f dash xi4. So you can see here, it is the same expression. It is the same expression. So T is, in fact, is your T star. I'm sorry, T star. So T star. What is T star? T star is given. T star is the point where these characteristics intersect. But we have just seen that characteristics intersect. Okay. When characteristics intersect, what happened? We have obtained this expression. T is equal to minus 1 upon f dash. This is the same expression, you see. 1 upon f dash. It means what? You see, if the profile develops a vertical slope, in the xt plane, it corresponds to the situation that the characteristics issuing from these 2 points intersect. Hello? This is the meaning. This is your ux plane, this is your xt plane. So we have just seen that the time when this characteristics showing from Xi3 and Xi4, they intersect, this is precisely the same time when the profile develops a vertical slope in the UX plane. Hello? Is it all right?
Yes, sir.
So this is an important result that when the profile develops a vertical slope, the characteristics issuing from different points, right? They intersect in the region. They intersect in the region. And in fact, what happens, the situation is now somewhat like this. From this part of the profile, the characteristics diverge. But from this part of the compressive phase, yes, they converge. So situation is somewhat like this, right? So you can find out that what is the minimum value of T. This is, suppose here you can see here, for example, here the characteristics, they break first at this point, right? This here the value of T, this is your XT plane. So here the value is lower, right? The minimum, we would like to know what is the first breaking time. Because in this region, is it clear to you? I should take another. Yes. The situation is like this, that here you see the characteristics, they diverge. But after, when you see these are the characteristics issuing from compressive phase, they start, this is the behavior. So you can see here, the situation is somewhat like this. So if this is the situation, this is your XT plane. This is your XT plane, right? The characteristic issuing from the expansive phase, they diverge. We have a perfectly continuous solution. But if you look at the compressive phase, then characteristics, they converge in the plus T direction and they are, right, they intersect. So you can see here, they intersect. So at the point of intersection, what happens? This characteristics takes some value from the initial data. This characteristic takes another value. So at this point, at the point of intersection, it is right, the solution is not single value, it is multiple value. Is that right? So the uniqueness of the solution gets lost. Here is a multi-valued solution. So we would like to know what is the time when that develops a vertical slope first. For example, so it is maybe clear we have to find the minimum value of T. T is equal to minus 1 upon F dash. We have obtained this expression. What is F dash? We have just said that F dash is nothing but C dash. What is C? C is a function of U. So in fact, it is a function of U naught Xi. It is a function, I did not write it, but it's understood, but should not create any confusion. Don't take that as if it is multiplied into its derivative, into U naught dash Xi. So in fact, I will write like this, that C dash into U naught dash. This is better. It is understood that C is a function of U naught dash, right? U naught Xi. So this is the expression for F, right? So it is clear from here that this time, right, this is to be minimized. I want to know that what is the minimum value of T. This is the minimum value of T. If I take this as T, you can see here that in this part, right, in this strip, you have a perfectly continuous solution. This is the first breaking time. Here the solution is of class C1. The first breaking takes place, suppose this is your T is equal to TB, this point. So it means when T is greater than or equal to 0, is less than TB, the solution is C1. The solution of the initial value problem is C1. Beyond this, now it's a multi-valued region. So it's all right. I can say that the solution is of class C1 here, right? This is something which is very important. So let us take an example of, then perhaps it would be understood in a better way. I take this as UT plus UUX, this is equal to 0, right? And the initial profile at T equal to 0, which I call U naught X, it is given as 1 upon 1 plus x square. So if you look at here, x is in R, and here of course t is. So you can see here, how does it look like? It is very clear. The initial profile, if you look at the initial profile, when x tends to plus minus infinity, it goes to 0. So the profile is somewhat, at x is equal to 0, it is 1. So the profile looks like this. Is that right? This is our initial profile, u naught x. Hello?
Yes, sir.
And if you look at this, is it linear, quasi-linear, non-linear? What is the nature of this? Hello?
Quasi-linear, sir.
Yes, quasi-linear. Why it is quasi-linear? Because it is linear in the height.
Linear in ux and ut and non-linear in u.
Very right, it is quasi-linear. But a very special case. Here, you see, we considered the equation just now, ut plus c of u into ux. This is equal to 0. C is some function of u. So in fact, it's a very special case that c of u is nothing but u itself. This is called Burger's equation. Burger's equation. You see, the difference between linear and non-linear, quasi-linear lies in the fact that, you see, for quasi-linear, the c is a function of u. This is a very special case of this. The dependence, so distortion takes place only because of this, because c depends on u. The dependence of c on u, it produces a distortion of the initial profile. We have seen that the initial profile undergoes distortion during the course of propagation. It is on account of this fact that c is a function of u. Is that right? Hello? Is it okay?
Yes.
So this is a very special case of this equation, and this is called Burger's equation. A very, very important partial differential equation. You see, only in 60s. All these ideas were known in mechanics, you see, at one point of time, but with the help of this simple model, because this is a fantastic equation. It exhibits genuine nonlinearity. It exhibits genuine nonlinearity because, right, dependence of c on u is called genuine nonlinearity. This nomenclature was given by Lex, who is still alive at Courant Institute of Mathematical Sciences in New York, right? Still alive. So this term was given by, Professor Lex. Burger's equation. Burger's used this equation, you see, in modeling turbulence. So this equation became very famous in 60s. Large number of papers, they were based on this differential equation. All right, so let us see what happens to this equation. Very interesting. We would like to know what happens to the solution. This is your space curve, and this is the characteristic, right? We are using the method of characteristics. So what are the characteristics? The characteristics are obtained, dx, ds. This is your, tell me what is dx, ds? Hello?
U.
Very nice, very good. This is your u. What is dt, ds?
1.
1. Very good. And what is du, ds?
0.
0. Very nice. And what is the space curve? A space curve is this. That is, I can parameterize it. X is equal to xi, t equal to 0, and u is equal to u naught x, u naught xi. That is 1 upon
1 plus I square.
1 upon 1 plus xi square. Excellent. Very good. I told you what is the methodology. Cauchy problem is solved, right, by considering characteristics emanating from points of gamma, right? So these conditions are taking on s is equal to 0. This is the point, s is equal to 0. P is any point here. P, this is the point whose coordinates in the s-xi plane, right? Xi coordinate is, this is xi and s is 0. It emanates from this point. All right. So what do we get? First of all, you can see that what happens to this Jacobian? dx dxi. dx dxi is 1. What is dt dxi? 0. What is dx ds? Dx ds at s is equal to 0. I want at s is equal to 0. Tell me quickly what is dx ds at s is equal to 0? Hello? I want this as dx ds and dt ds at s is equal to 0. I want these expressions. So tell me dx ds. What is dx ds at s is equal to 0?
0.
Yes, please.
Is 1 by 1 plus I square.
1 upon 1 plus xi square. U is 1, so 1 upon 1 plus xi square. And what is dt ds?
Is 1.
dt ds is 1. So what is this Jacobian?
Is 1.
1.
Not
Which,
0.
And 1.
so quickly we can say,
Unique.
so what will
Unique
be-
solution.
Unique solution, wonderful. There is no need of finding, yes, whether gamma is characteristic or not, whatever it may be, it has a unique solution. Is that right? If the determinant of the coefficient matrix is different from 0, the linear system, I mean, two equations involving two unknowns has a unique solution, and it follows that there exists a unique solution of class C1 where in the neighborhood of S is equal to 0, in the neighborhood of space curve.
Yes, space.
Very good. In the neighborhood of gamma. So look here, in the neighborhood of gamma, we have a wonderful situation. It is the solution is of class C1. It is precisely like this. You see, at t equal to 0, this is the thing. At t is equal to TB, yes, solution breaks down. But between 0 and TB, you have a unique solution which is of class C1. This is precisely happening like, right? It is quite possible that beyond this, the solution may not be unique. It is quite possible. Solution may not be unique. Solution may not exist. Solution may break down. So let us see what happens. So it is very clear. We have just seen that what is the breaking time now? Hello, we can find out what is the breaking time. Breaking time we have already determined. We can write down the solution. The solution is going to be the same form that u is equal to, right? It is very simple now. Solution, smooth solution I can write. How to write this smooth solution? Tell me quickly. Integrate these equations. So what do you get? T is equal to, u is equal to constant. Let us start with this. U is equal to constant. U is equal to constant, is that right? And
Yes, sir.
constant at s is equal to 0 is 1 upon xi square. Is 1 upon 1 plus xi square. So u is equal to 1 upon 1 plus xi square. Am I right? U is equal to constant, which is u naught xi, and u naught xi, in fact, it is given by this expression. What is t? Tell me quickly. T is equal to s, and at s is equal to 0 plus some constant. That constant can be determined using this condition. At s is equal to 0, t equal to 0. So that's all. That constant turns out to be 0. Now you tell me, what is x? Hello?
Yes, sir.
From here, now can we find out what is x?
Yes. Yes.
Tan inverse.
X is nothing but the integral of u, and u is a constant. Is that right? U is a constant. Am I right? U is equal to u naught xi. It's constant. So x will be your s. Am I right? X will be your s times u naught xi. I know what is u naught xi. It is u naught xi is 1 upon, yeah, right, 1 upon 1 plus xi square plus some constant. What is the value of that constant?
Because x is this, x is xi.
Excellent, excellent, very good, nice. Because at s is equal to 0, x is equal to xi. So very good. So it is very clear because the Jacobian is different from 0. So I can, these correct, you see, what is this? It is the locus of a point which depends on two parameters, s and xi. And in fact, it represents a unique surface because Jacobian is different from 0. So it means what? I can solve these equations for s and t. So it's very clear that s is your t. Hello? S is your t. And similarly, psi I can determine because u naught psi is given by this expression. So both psi and s substitute here, right? Eliminate this, you get the solution. So solution is completely known. Now breaking time. What is the breaking time? Hello? I have just obtained the breaking time. What is the, definitely it is going to break. The theory says that it is quasi-linear, right? What is the breaking time? T is given by this expression, minus 1 upon f dash. Hello?
Yes, sir.
So minus 1 upon f dash. What is f? F dash is this expression.
Yes.
F dash is this expression. So let me write C dash. What is C here in this case? C is nothing but U.
U.
So C prime means dC du.
DC.
1. Is that right? You see? C is C of U. And
Yes.
it's nothing but U itself. So what will be C dash? C dash will be
1.
good. And then what do you get? What is the second factor? Yes.
U.
F dash. F dash is u naught dash xi. So u naught is given by this expression. This is u naught xi.
1 over 1 plus x.
So I have to differentiate it, right? U naught is this. It is u naught dash. Dash means its derivative.
Yes.
It's a function of xi. Means this is to be differentiated. So
minus 2 over.
very good. Nice. Xi, and this will be in the numerator. Am I right? Please check. Is it correct?
Yes, sir. Yes, sir.
Very good. Is it all right? Hello, all of you agree that this
Yes,
is
sir. Yes, sir.
very nice. Now I want to find out what is the minimum value of this. How to find out the minimum value? In calculus, I know it is a function of xi. Yeah, right? For minimum, first derivative should vanish. Yes or no?
Yes, sir.
Yes, yes, sir.
So very nice. The first derivative. So forget 1 by 2, it is all right. So xi into its derivative, that is 2 into 1 plus xi square into 2 xi, right? This into its derivative minus 1 plus xi square whole square into its derivative is 1 divided by this. This should vanish. Is it all right? Hello?
Okay.
Yes,
Yes,
sir.
sir. Yes, sir.
First derivative. So from here, what do we get? You can see here that 4 xi square. Am I right?
Yes, sir.
This factor, in fact, yes, because this is different. Get rid of this 1 plus 1 factor. So what remains? 4 xi square minus 1 plus xi square. This is equal to 0. And this gives me what? 3.
Xi square is equal to 1 over
3
3.
square minus 1 equal to
Very right. Good. Xi is equal to, so
Minus 1.
plus minus 1.
Plus minus 1 over 3.
Plus minus 1.
very right. So you tell me which value of xi is to be taken. There are two values. Xi is equal to plus minus 1 by root 3. Which values?
Check
Hello?
to 1 by 3.
The plus sign or minus sign?
Plus sign.
Why?
Minus.
Simple, because it is time. Time is positive.
Means positive. Yes, yes, sir.
Yeah, very good. So this is your, at xi is equal to 1 by 3. So we get 1 plus 1 by 9 whole square divided by 2 into 1 by root 3. Can you quickly tell me what is this? Am I right? I committed a mistake.
Excuse me, sir.
Yes.
In the numerator, we have taken 2 xi. So, when you differentiate the denominator, you get 2, sir.
Yes, sir. So xi should be plus minus 1.
So, xi is plus 1. Am I clear? The differentiation of that u by v, the numerator, 2 xi, when you differentiate that, you have right, that is correct. Then minus numerator, when you differentiate the denominator, it is 2 xi.
I have forgotten. This concept does not contribute anything.
Then this 2 should not be considered, sir.
To appear
Missing.
xi into derivative of this. Oh, xi into derivative of 1 plus xi square whole square. I have written here. Xi into derivative.
Yeah,
But
yeah.
second, sir.
But that's a minus 1 plus xi square whole square.
Very
Two,
right.
two.
Into 2. Into 2.
Into 2. 2 is missing.
If you
Yeah.
taken that 1/2 common,
Oh my God. Arey, TB
so
is,
that,
you forget this half, we will take care of this half later. What is the function?
Okay, okay, sir.
okay, so then the first term the 2 should not come.
Yeah, yeah.
First term 2 should not come.
Come. Sir, the
The numerator.
above.
Numerator.
Yeah. 2 xi, the 2 should not be there.
Because you are not taken into account.
No, I am
It is
differentiating.
clear. It is clear, sir.
I am differentiating this with respect to xi. So 2 will be there, Baba. 2 into 1 plus xi square. 2 into 1 plus xi square into 2 xi.
Yes, sir. Yes, sir.
Yes,
You
sir.
are
Yes, sir.
correct.
Getting.
Yes, sir,
We are
correct.
getting.
Into xi, not to the.
Okay.
Is it all right? Hello?
Yes, yes, sir. It's all right.
Because the right hand side is 0,
Yeah,
doesn't
correct, sir,
matter.
correct.
I think everything is fine. There is
Yes, yes.
no mistake. So it is all right. So put xi is equal to 1 by root 3. So 1 plus 1 upon 3 divided by, now of course 2 is there. I will take this 2. And 1 by root 3. Is that right? So what you get? 3 plus 4 by 16 by 9. Am I right?
Yes.
16 by 9 and root 3 by 2. That is 8 by 3 root 3. Am I right? Hello?
Yes, sir. Yes, sir. Yes, sir.
Under root 27. So look here, I am able to find out that what is that strip in which you get it. That is in the neighborhood of this, there is a unique solution. This is at t equal to 0. In the neighborhood, there is a solution of class C1, but at TB, that is at t is equal to TB, and this TB turns out to be 8 by under root 27. That is, here the solution breaks down. The first breaking point appears here. So in this open interval, the solution is of class C1. Is it all right? Hello?
Yes, sir. Yes, sir.
So it's a beautiful example. There is a book by Breshan. You will find this example in Breshan's book. Breshan he's an outstanding mathematician, you see, at Pittsburgh, University of Pittsburgh. Currently, he is the recipient of several awards. He is working on partial differential equations, especially these quasi-linear hyperbolic systems. So he has written a book, and this example, in fact, is from that book. I have taken it. So I have already told you that which are the books perhaps you can think of.
Yes, sir.
I'm sorry that yes. Now it is visible. I'm sorry that yes, it was not visible. All right.
So what is the final value of TB dash to turn out to be?
Final value of
TB double dash.
8 by under root 27.
8 by?
Under root 27. 3 root 3 I can write under root 27. Am I right? This 3 root 3 can be written as under root 27. Same thing. Either you retain this 3 root 3 or you write under root 27. Same thing. Hello?
Yes, sir.
That's same.
Same, yeah, very right. So is it all right? Is it clear?
Yes, sir.
Yes, sir, it's clear.
So we have, yes. All right. So these two are important things. So a very important result, you see, we have arrived at. What is that important result? If your initial data, this breaking time, the breaking time is given by 1 upon C naught dash, C dash into U naught dash xi. This is the breaking time. Okay. This is your breaking time. So clear that what is C? C is a function of U. C is a function of U. And it's clear. And what is U? If you remember, X is equal to xi plus T times F xi. This is your, and U is equal to U naught xi. This is the solution, right? This capital F, the capital F is C of U of xi. This is your analytical form of the solution. Do you recall? X is equal to xi plus T times F of xi. U is equal to U naught of xi, where capital F is given by this expression C of U of xi, right? And we have found that after a finite time given by this expression, what happens? the continuity of the solution breaks down. What happens? What does it mean? The gradients become infinite. Ux and ut, they both become unbounded. They both become unbounded. Hello?
Yes, sir.
Any clarification? Any query from anywhere? Hello?
No, sir, it's clear.
No, sir. No, sir.
All right. So, so look here, if your initial data is such that, your U is bounded, is that right? What is U? U naught? U naught is your initial data, it is given to you. U at t equal to 0 is U naught. This is given to you. What is X? X is in R. So if U naught is bounded, that is maximum of U naught, if it is capital N, is that right? C is a function of U, so C dash, right? C dash, that is maximum. So I can say that maximum of U naught dash, because it's a bounded function. So maximum of U naught dash, suppose it is your L, right? And maximum of C dash, the domain of C is nothing but U. So I have to maximize, it is on R, right? Here maximum is to be taken on because the domain is U and U takes values minus M2 plus M. That is this closed interval minus M2 plus M. So if these entities, right, if they are bounded, let us say capital N, then I know TB. TB in fact is always less than 1 upon, right? What do we get? C dash, that is your N, and U dash, that is your L. So what a wonderful result. This is a theorem, very simple theorem, but quite apparent. You see, from this result, it is quite apparent that if these functions are bounded, what does it mean? If the Cauchy data is globally bounded, that is, if the Cauchy data is globally bounded, globally smooth and bounded, then the breaking time is given. I can find out what is the breaking time, right? That is, look here, it has the initial value problem has a smooth solution in this interval, 0 to TB, right? This is your T direction and this is your X direction. In this region, there is a smooth solution. T varies 0, less than or equal to T, less than TB, and TB is given by this expression. A very important result. Again, you will find its proof in Breshan's book. Okay, but the result is very important and it is quite apparent also. If I can find out, so if the Cauchy data is globally smooth and bounded, I can quickly find out what is the breaking time. All right, so this result is quite important. Now the question arises, right? Now, can you tell me now, I ask you a question, this breaking takes place on account of what? What is that which causes this breaking? Hello? In linear case, no breaking, right? No breaking. In quasi-linear case, I have seen that there is a breaking.
Breaking.
Why this breaking takes place? Hello? Why this breaking takes place? This breaking takes place because of the intersection of characteristics.
Yes.
This is the main reason. You see, these characteristics which do not
Yes.
intersect here in this region,
Yes.
but outside this they can intersect. See?
Yes.
Like this. If the characteristics is showing from different points of this space curve, if they intersect, then at that point the solution becomes discontinuous. And what happened in this strip, you have a perfectly smooth solution, but outside this, it's quite possible that the solution may break down, and this is precisely happening here. Is it all right? Let us see what happens in semi-linear equations. Semi-linear equations. Let us take a very simple case of a semi-linear equation, say ut plus ux is equal to u square. Oh, is it semi-linear? Are you sure? Hello? Please tell me whether this differential equation is semi-linear.
It's semi-linear.
Very good, very nice. Okay, and I take the initial, so x is, of course, I take this x to be positive, it's all right. I can take this to be positive, and u, or in fact, there is no need of putting this condition, x, I will take x as an r, it is fine, x is an r, and initial profile, I need x at t equal to 0. Suppose this is your cosine of x. This is your initial value problem. So in fact, the solution of this, yes, can be determined. Yes. What is the procedure? We have already discussed the procedure. Cauchy problem. Cauchy problem. What are the characteristics? Quickly tell me. Dx, ds.
One.
Good, 1. What is dt, ds?
One. This also one.
Very good. And what is du, ds?
U square.
U square.
Very nice. And what is the space curve? This is your space curve, right? A space curve is, yes, I can parameterize x is equal to xi, t equal to 0, and u is equal to
Cos j. Cos j.
Cos Z.
and I take these values, right? These characteristics, they emanate from the points of gamma. Characteristics, they emanate from the, so at s is equal to 0. So this is an initial value problem. So the problem of solving this partial differential equation, this initial value problem involving a partial differential equation, reduces to the problem of solving a system of ODEs, right? Satisfying this initial condition. Quickly tell me, what is x? X is your s, constant. And what is that constant at s is equal to 0?
Psi.
Psi, good. T is equal to s. And what is that constant plus constant at s is equal to 0? T is
Constant is 0.
Zero, zero.
very nice. And here I can integrate minus 1 by u is equal to s plus some constant. What is that constant?
Cos z.
This is equal to minus 1 upon, hello? Am I right? What is the,
Yes, sir.
wow,
Minus 1 by cos z.
minus 1 by cos xi, minus 1 by us, yes, minus 1 by cos xi. Correct. All right. So we can find out, look here, it's very clear that s is equal to t and xi is equal to x minus t. S and t, s and xi can be solved. So even this is the feature, definitely Jacobian of the transformation is different from 0. You can see here. What is g xi 0? J, Jacobian of the transformation. It is your dx d xi. It is your dt d xi. It is your dx ds. It is your dt ds. Tell me quickly, what is this expression? Dx d xi. Dx d xi is 1.
1,
1.
0,
0.
It is
1, 1.
1.
1. And t is
1.
Yes.
Equal to 1, not 0.
and therefore a unique solution in the
Solution.
unique solution where in the neighborhood of this is the point s is equal to 0. S is equal from here. So at this point P, whose coordinates are 0, that is in a small neighborhood of this. You see, we get only a local solution. We really do not know. So it's a smooth solution. So it's very clear that the solution in the neighborhood of gamma, the Cauchy problem has a unique solution. Cauchy problem has a unique, smooth solution in the neighborhood of gamma space curve. This is the result. But really, you don't know this. What happens after this? When we move away from that neighborhood, right? When we move away from that solution will tell us. The solution will tell us. So can you tell me what is u here now? You will, so S is your t, put S is equal to t, and xi is your x minus t.
Minus 2.
So can you tell me quickly what is the form of u in terms of these functions? Hello? You can do calculation faster than me. 1 by u will be your 1 upon cos xi minus s. Am I right? From
Minus t.
this is your 1 minus s cos xi divided by cos xi, and u will be your cos xi divided by 1 minus s cos xi. Am I right? Hello? Is it all right?
Yes, sir.
Yes, sir. Yes.
Very good. So now we know that xi and s, they have been computed in terms of s and
S and
t.
T.
So uxt will be your, I'm sorry, uxt will be your what? Sine of xi. Xi is your x minus t. Am I
Yes.
right? X minus t divided by 1 minus
1 minus
t. This is your t. Am I right?
T. Yes.
Sine of x minus t. So look here, this is the solution. This is the solution at any time xt. What do you infer? Hello? What do you infer from this form of the solution? Can you tell me? Is there, yes? What are the consequences? Can you draw some consequence from here? The solution at any time t is given by this expression. Look at the denominator. What happens? Look at the denominator. What happens? When t is equal to, hello, when sine of x minus t, because cosine is a bounded function, right?
Yes.
No matter what x minus t is, the cosine function is always bounded. When cosine of x minus t is 1 by t, yes, then there is a problem. Yes or no?
Yes, sir.
What happens? U becomes unbounded. Becomes unbounded. U becomes unbounded. What happens in quasi-linear? What did we notice? Do you remember? Gradients become unbounded, not U. U remains finite.
Yes.
In quasi-linear, U always remains bounded. U remains bounded. But UX and UT, they become unbounded. Right? As t approaches t. But here in semi-linear,
Q becomes unbounded.
U itself becomes unbounded. Is that right? Hello?
Yes, sir.
The solution becomes unbounded. So in fact, solution blows up. Solution blows up. And what happens? You can see here, at time say t is equal to 1. What happens when t is equal to 1? When time, yes, t is 1, what do we get?
Cos
Cosine of x minus 1 is 1. And this gives me x is equal to c plus minus 2 n pi, right? N is equal to 0 plus minus 1 plus minus 2. Am I right?
Yes, sir.
X is equal to 0. Is it all right? Hello?
Yes, sir. Yes.
So x is x minus 1, that is
1.
equal to 1. So x is equal to 1 plus 2 n pi. Is that right? Hello?
Yes, sir.
Okay, so look here at this distance, running after a running length of 1 plus 2 n pi. So you can see here that n is equal to 0 plus minus 2. At all these points, the solution becomes unbounded. Is that right? The solution exhibits a blow up, right? At t is equal to 1 at all these points. This is the cosine function. Am I right?
Yes, sir.
Your cosine function at t is equal to 1, you find that these peaks, in fact, at t is equal to 1, the solution becomes unbounded. So a very different feature from quasi-linear and linear. But here characteristics, they don't intersect. No, characteristics, they never intersect. It is clear from here. Hello? So,
Yes, sir.
you see, these three equations, they have different features. You should always keep in your mind. In linear case, there is no distortion. There is no distortion in the linear case, right? In the quasi-linear case, there is a distortion, and this distortion because characteristics, they start converging or diverging. That is the nature. As a result, it undergoes the distortion. And in semi-linear equation, it blows up. There is no, I mean, the non-linearity, this blowing up. You see, this feature, when gradients become unbounded, we say that the solution is experiencing a gradient catastrophe. There is a name for it. The solution develops a gradient catastrophe. But here the solution blows up. There the gradients blow up, right? So these are different features. I think time is up. I have taken enough time. I'm sorry that somebody would be waiting for the lecture. I'm very sorry.
No, sir. It's okay, sir.